Okay everyone, this is going to be 2.3 thermal capacity calculations. Look at the first question here. What do they want from you? A block of copper has a mass of 2 kg. This is going to be a mass. The block can absorb up to 12,000 joules. This is obviously going to be your thermal energy. The specific capacity of the copper is this amount. This is your specific capacity. What is the rise of temperature of the copper, which is obviously your theta here. Since we understand that Q is equals to mc theta, theta will be equals to Q over mc here. In this case, it will be 12,000 divided by 2 divided by 385. Press that into the calculator. 12,000 divided by 2 divided by 385. You're supposed to get 15.6 degrees Celsius here. Alright? And after that, moving on to the next question. In an experiment, an object is heated. The data from the experiment is shown. The energy transferred to the object is 3 kJ, which is 3,000 joules. Right, this is going to be your energy. The mass is 2 kg mass. The rise in temperature is 10 degrees Celsius, and the specific heat capacity of the object is going to be this amount. Specific capacity this amount. What is the thermal capacity of an object? Now, if you can recall, specific heat capacity is Q equals to mc theta, whereas thermal capacity Q is equals to Tc theta, right? So in order to find thermal capacity is basically Q over theta here. In this case, it will be 3,000 divided by 10, which is going to give you 300 joules degrees Celsius. Now in your exam, if you forget about the formula for thermal capacity, you can always look at the units given here that in the answers. If it is joules per degree Celsius, then obviously it is joules per degree Celsius, which is Q over theta here, which in this case will be 3,000 divided by 10. So that's why you're supposed to get B as your answer here. Alright. Okay, looking at question 4, what do they want from you? A block of iron, mass M, is heated and gains 10,000 kilojoules of internal energy. The temperature rises by theta degrees Celsius. A second block of 2M is heated and gains 5,000 joules of internal energy. What is the rise of temperature in block C here? Now there is two ways that you can do this. The first method you're going to do it is relatively easy. It's by comparing two of the equations. Looking at the first statement here, I can form the equation Q equals to mc theta, right? Q is equals to mc theta. In this case here, it will be 10,000 joules is equals to M, capital M, then C, specific capacity of iron, and the theta given here. Looking at the second equation, this one here is asking us to find theta, right? So yet again, we can form Q equals to mc, which in this case here will be 5,000 equals to double the mass C and then theta, which is X that we're looking for. Now today, if I'm looking for X, right, I can make X the subject here, and I can find that X is equals to 5,000 divided by 2 mc here. Whereas if I make theta the equation, the subject here, I'm going to get theta is equals to 10,000 divided by mc here. Now today, if I want to compare these two things here, is quite straightforward. Looking at this equation here, if theta is equals to 10,000 divided by m and c, when I have half the energy, can you see from 10,000 to 5,000, it's divided by 2, right? My theta is naturally going to divide by 2. And then when I double the mass, because when I double the mass, it's going to be harder to heat up as well, right? So here I have to double it up again, right? So at the end of the day, I'm going to get X over 4 is going to be my answer here, which is theta over 4 here. Now the second method you can do this is by comparing the two specific capacities. Since both of them are the same iron, right, then I know for a fact that both of them should have the same specific capacity. Making specific heat capacity the subject here, C will be equals to Q over mc, right? And in the first statement here, it's going to be 10,000 is equals to double the M theta, double the m, m, multiply by theta here, right? Looking at the second statement, since they are the same ion, I know that C is going to be equals to 5,000 divided by double the mn theta here as well, which is the one that I'm looking for. X lah, let's make it X here, okay? If I compare these two, since this is C and this is C, right, I can actually equate these two things together, and making X the subject here, I'll be able to find that theta will be equals, the theta will be divided by 4 as well, which is yet again going to be A. So it depends on what you're going to do lah. If I were to go for the full equation here, it will be something like 2mx over 5,000 is equals to m theta over 10,000. Making x the subject here, it'll be 2mx is equals to 5,000 divided by 10,000 multiplied by m theta. Then after that, x will be basically half times m over 2 theta here, which at the end of the day, sorry, no more m because the m's are going to cut. There will be no more m here. It will just be 1 again. So at the end of the day, x will be still equals to 1 over 4 theta here, which is yet again going to be A. So it depends on which method you want to use. You can either equate both of the C's together since they are of the same material, or you could just compare the first statement, the first equation with the second equation here. Then you'll be able to find that the theta is going to be divided by 4. Okay? Then looking at question number 5 here, a block of ice is at a temperature of negative 100 degrees Celsius. Energy is supplied at a constant rate. The graph shows how its temperature changes. At which point has the ice completely changed to water and all water completely changed state into steam. Now in order for it to completely change state, is basically going to be here and here, right? Because if this is solid plus liquid, this is fully liquid, this is liquid plus gas, and then this is fully gas, right? So completely changing into water is definitely number 2, and completely changing into steam is definitely number 4 here. So answer is donkey in this question. Alright. Then question number 6, the temperature of the water at the bottom of the waterfall is greater than the temperature at the top. So there's the waterfall here. The temperature is higher, the temperature here is lower. The gravitational potential energy of the water at the top is transferred to thermal energy at the bottom, so potential energy is converted into heat energy here. The specific capacity is this amount. What is the temperature difference of the height at 21 meters here? So if I understand the potential energy is equals to heat energy here, I can make mgh equals to mc theta, which are both the equations. Since there's both m on this side, I'm going to cut it all off. And from here, I can start substituting all the information I have, right? The gravity is going to be 10 multiplied by the height of 21 is equals to your c, which is 4,200 multiplied by your theta. So essentially your theta is going to be 210 divided by 4,200, which is going to give you B as the answer, guys. It's just a simple play of algebra here. Then look at the next question. Figure 4.1 shows a cold plastic spoon that has been placed into hot liquid in a cup. Okay, cold plastic spoon, hot liquid in the cup. The cup contains 150 grams of liquid, which is 0.15 kg here. Specific capacity is this amount. Oh, sorry, don't change it into kg because the specific capacity is already in grams. So you don't have to change this. When the cold spoon is placed into the hot liquid, the temperature of the liquid decreases from 80 degrees Celsius to 56 degrees Celsius. I know that the theta here is going to be 24 degrees Celsius. Calculate the loss of thermal energy. Is essentially Q equals to mc theta here. Q will be equals to 150 multiplied by 4.2 multiplied by 24. Press all of that into your calculator. You're supposed to get 15120, 15120 joules, which is going to be 1.51 times 10 to the power of 1, 2, 3, 4. 4 joules here. 1.51 times 10 to the power of 4 joules here. Right? And some of you guys may not be able to do this question again because there's current and voltage. It's supposed to be a year 11 question, but no worries. Let's look at what they want. The current in the heater is 3.8 amperes and potential difference is this amount. This is the current, this is the voltage. The iron of the block is 2 kg. When the heater is switched on for 10 minutes, time is going to be 600 seconds. The temperature of the block changes from 35 to 55, which is 30 degrees Celsius difference here. Calculate the specific heat capacity. Now, since I know Q is equals to MC theta, specific capacity here will be Q over M theta, right? In this case here, if I'm looking for Q, it's basically going to be energy. Energy is supposed to be VIT here. So it's supposed to be C equals to VIT divided by M theta. From here, substituting everything in is just 12 times 3.8 times 600 divided by the mass of 2 kg divided by the mass of, the change in temperature of 30 degrees Celsius. So yet again, you can press everything in the calculator. 12 times 3.8 okay, times 600 divided by 2 divided by 30 here. You're supposed to get a specific capacity of 456 joules per kg degree Celsius. 456 joules per kg degree Celsius here. Okay, and finally looking at the last question here. In the student's home, there is wood burning stove which is made of iron. The mass of the wood burning stove is 85 kg. State what is meant by thermal capacity. Yet again, if they ask you anything that relates to the formula, thermal capacity is supposed to be Q over theta here. So your statement is going to be the amount of energy needed to change 1 degree Celsius an object. The amount of energy needed to change 1 degree Celsius of an object. Okay, and then after that, the specific capacity of iron is 400 and blah blah blah. Right, this see here, calculate the thermal capacity. Now thermal capacity is supposed to be joules per degree Celsius, right? So if I have joules per kg degree Celsius, obviously what I have to do is joules per kg degree Celsius. I have to multiply the kg in order for me to cut it away lah. In this case here will be 460 multiplied by 85. Press that into the calculator. 460 multiplied by 85. You're going to get 39,100 joules per degree Celsius, which is 3.91 times 10 to the power of 1, 2, 3, 4. 4 joules per degree Celsius here. And this is how you're supposed to finish these kind of questions here. Alright. Moving on to the next question, next set of questions. We'll look at question number 1 here. A 1 kg of aluminum block requires more thermal energy to rise its temperature by 1 degree Celsius than 1 kg of copper, right? So if this one here requires more energy, it means to say it has a higher specific heat capacity than this one here lah, right? Why is this so? Aluminium is a better conductor of thermal energy than copper. Not true. Aluminium is a poorer conductor than thermal energy than copper. Possible. Aluminium has a higher specific heat capacity than copper. Not possible. Aluminium has a higher specific than copper. That's possible. Aluminium has a lower specific heat. That is not possible as well. So the more logical answer here is definitely going to be C as the answer. Right? Then 100 grams of water at 25 degrees Celsius is poured into an insulating cup. 50 grams of ice at 0 degrees Celsius is added. The water is stirred until the temperature of the water has fallen to 0 degrees Celsius. 18 grams of ice remain unmelted. The specific capacity is this amount. What value does this experiment give for the specific latent heat of fusion? Now there are a few parts to this question, and now first and foremost, this part here is basically from the water. This part here to this part here is basically the ice, and the specific capacity of water is this amount. In this question here, they're basically testing your understanding about thermal equilibrium. The amount of energy gained by the ice is basically the amount of energy, the amount of energy gained by the ice is the amount of energy lost by the water, right? In this case here, you're supposed to use the ice of Q equals to MLF is equals to Q equals to MC theta of the water here. Now, the M, however, is a little bit tricky. Since only 50 grams to 18 grams of ice was melted, right? It means to say that 32 grams of ice was melted. Looking for your LF here, I don't know what LF is equals to the mass of your ice, which is, your water, which is 100 grams, multiplied by the specific capacity of 4.2 multiplied by the degree Celsius of is 25 because it's going to be 25 to 0, right? Calculating everything into the formula, into the calculator here, is basically going to be 100 multiplied by 4.2 multiplied by 225 divided by 32 here, which is going to give you a specific capacity of somewhere around 330 joules per grams now, right? Because you have to take into consideration that only 32 grams of ice was melted, right? The same quantity of thermal energy is supplied to each of the floor blocks. Each block is made of different materials. Which block has the greatest thermal capacity? Yet again, thermal capacity is joules per degree Celsius, right? Since all of them have the same joules, whichever one has the lowest change in temperature has the highest thermal capacity, right? The lowest change in temperature is going to be A here. So your answer is naturally going to be A. Then moving on, an electrical heater is placed on the floor of a room in a house. The heater is switched on. The heater has a power of this amount. The air in the room has a mass of this amount. The specific capacity has a specific capacity of this amount. Calculate the time, I'm looking for the time taken for this heater to raise the temperature by 7 degrees Celsius. Okay, so from here, it's basically power is equals to energy over time, right? In this case here, time is equals to energy over power. And the energy in this case here is obviously going to be MC theta over power. In this case here, it will be basically 65 multiplied by 720 multiplied by 7, change in temperature, divide by the power of 1500. Press everything into the calculator again. You're going to get a time of 218.4 seconds, which is essentially 218 seconds here. Always remember to write it in 3 significant figures and include your units, guys. Alright. State 2 reasons why the time calculated in B1 is smaller than the actual time taken to raise the temperature of air in the room from 8 to 15 degrees Celsius. Now yet again, all these calculation questions are, whenever dealing with heat questions, all these calculated questions here are best case scenario. We're assuming that all the power is converted into heat energy. But in reality, we know that energy will never be fully transferred. It's going to be lost to the surrounding as heat and sound, right? So for here, you have to understand that these are the standard answers for any heat related questions are energy is lost to the surrounding during transference of heat, and energy is converted into other forms. And you could also say that energy is conducted to the walls of the room. The walls or the floor of the room. Okay, it's just another way to say that energy is lost to the surrounding. Alright. And looking at this next question here, what do they want from you? Figure 5.1 shows apparatus used to determine the power output of the heater. The metal block has a mass of this amount. You have a specific capacity of this amount. In time equals to 2 minutes and 30 seconds, which is going to be 150 seconds here. Change from a temperature of this to this amount, which is going to be 18 degrees Celsius here. Calculate the power. Power is essentially going to be energy over time. In this case here, it's obviously going to be MC theta over time. In this case here will be 2.7 multiplied by 900 multiplied by 18 divide by the time of 150 seconds. Press everything into the calculator. You're going to get a power of 291.6, which is 292 watts. 292 watts here. State and explain a precaution that can be taken to improve the accuracy of this experiment here. Now, whenever we're talking about all these improvements, it's basically to prevent heat loss from the block, right? So it's always to add on another layer of insulation so that heat may be prevented from losing to the surrounding. And your statement is going to be statement is to add insulation to the metal block, and your explanation is because to prevent heat loss to the surrounding. Okay, that's how you get your 2 marks here. And then looking at the final 3 questions. Figure 4.1 shows a heater in a metal block. The power is this amount. The switch is, the time taken was this amount, which is times 60, 240 seconds here. The metal block has a specific capacity of this amount and a mass of this amount. Calculate the increase in temperature, which is the theta. So yet again, power is equals to energy over time, right? Power will be equals to MC theta over time here. Power times time is equals to MC theta, and theta would have been power times time over MC, which is going to be 370 multiplied by 240 divided by 5 multiplied by 420 here. Press everything into the calculator. 370 multiplied by 240 divided by 5 divided by 420 here. It will be exactly 42.3 degrees Celsius. 42.3 degrees Celsius here. Alright. Okay, then moving on to question number 4. Thermal capacity. A student carries out an experiment. The block is heated for 23 minutes. It's basically 23 times 60. 23 times 60 would have been 1,380 seconds. The current in the heater is this amount, the voltage is this amount, and the change in temperature is 20 to 70, which is 50 degrees Celsius. Calculate the thermal capacity. Thermal capacity is yet again Q over theta. In this case here, energy will be VIT over theta here, which in this case will be 12 times 3 times 1,800 divided by your theta of 50. Press this in the calculator. 12 times 3 times 1380 divided by 50, which is going to give you a thermal capacity of 994 joules per degree Celsius. 994 joules per degree Celsius here. Okay, 994 joules per degree Celsius. And finally, looking at the last question here. At 3.5 minutes, the temperature of water reaches 100 degrees Celsius. The volume of the water is this amount with the density this amount. The specific capacity is this amount. calculate the thermal energy gained by the water. Oh, do I have enough information? Thermal energy Q is equals to MC theta. In this case here, density is equals to mass over volume. Mass will be equals to density multiplied by volume, which is going to be 1 times 1700, which is 1700 grams. Okay, change that into kg, which is 1.7 kg here. I have this, I have this. Oh, yeah, thermal capacity in this case here, Q will be equals to M 1.7 multiplied by 4200 multiplied by 100 degrees Celsius. Press this into your calculator. 1.7 multiplied by 4200 multiplied by 100 here. You're supposed to get a very large number, which is going to be 7.14 times 10 to the power of 1, 2, 3, 4, 5 joules here, guys. And this is how you're supposed to solve this question. Okay, always identify all your information and start forming your formulas. Okay, finishing off with the last set of the exercise here. If you look at the final question here, the specific capacity of aluminium, iron, ethanol and water are given. 1 kg of metal is put into 5 kg of each liquid. The starting temperature of each metal is 60 degrees Celsius, so it's going to be 60 here, 60 here. And the starting temperature of each liquid is going to be 10 degrees Celsius, is 10 degrees Celsius here and also 10 degrees Celsius here. Which example has the highest final temperature? Now, in order to have the highest final temperature, obviously what's going to happen is I want this metal to decrease temperature by very little. In order for this temperature to decrease by very little, I must have a relatively higher specific heat capacity. Okay, sorry, I had a call just now. Like I was saying, guys, if I want this thing here to be high temperature, I need this to lose the least amount of temperature. In order to lose the least amount of temperature, the specific heat capacity should be relatively higher, right? So that it doesn't change much in temperature lah. Whereas for the liquid, I want the liquid to have a more change in temperature. In order to have more change in temperature, my specific capacity should be relatively lower lah. Right, so looking at this question here, higher specific capacity for the metal is going to be aluminum. Lower specific capacity of the liquid is going to be ethanol. So that is why the answer is supposed to be A in this question here. Alright, then moving on to the next part, define the specific latent heat of fusion, and you'll see that it's 2 marks. Latent heat of fusion, Q is equals to MLF, right? LF will be basically Q over M lah. From here, it is the amount of energy needed to change 1 kg of a substance from solid to liquid without any change in temperature. The key word here is always without any change in temperature. So the amount of energy needed to change 1 kg of a substance from solid to liquid without any change in temperature. Keyword here is always without any change in temperature, guys. So make sure to include that now. Then, looking at the next part here, a small piece of 0 degrees Celsius added to 0.35 kg of water. The initial temperature of the water is 24 degrees Celsius, 0.5 degrees Celsius. The temperature of the water decreases to 0. The water loses 35,000 joules. The specific latent heat of ice is this amount. First question, they ask you for the specific heat capacity of water. Q is equals to MC theta. C is equals to Q over M theta. In this question here, Q will be 35,000 divided by the mass of 0.35 divided by the change in temperature, which is 24.5 to 0 lah. So it's 24.5 here, right? So press that in the calculator, 3500 divided by 0.35 divided by 24.5 here. press that in the calculator and you'll get a specific capacity of 4080 joules per kg degree Celsius. 4080 joules per kg degree Celsius. Then after that, they want you to find the mass of the ice added to the water. From this question here, yet again, you have to understand that the amount of energy lost by the water is the amount of energy gained by the ice. So from here is basically Q equals to MLF. You know, M will be equals to Q over LF. Sorry, over LF, which is going to be 35,000 divided by 3.3 times 10 to the power of 5. Press that into your calculator. 35,000 divided by 3 divided by 10 to the power of 5. You're supposed to get a mass of 0.11 kg, guys, or more accurately 0.106 kg. Okay, then moving on to the next question. Water has a specific capacity of this amount. The boiling point is this. The mass is this here of water is boiling is poured into copper container, which initially is 11 degrees Celsius. After a few seconds, the temperature of the container both reach 95 degrees Celsius. First and foremost, they ask you to calculate the energy transferred from the water. Yet again, this is going to be a Q equals to MC theta question. The M is going to be obviously 0.3. Your specific capacity is 4,200. And your change in temperature is essentially going to be 5. Right, because it's the water is going from 100 degrees Celsius to 95 degrees Celsius. So from here, 0.3 times 4,200 times 5, you're supposed to get an energy of 6,300 joules here. Okay, then after that, calculate the thermal capacity of the copper. Thermal capacity is yet again Q over change in temperature. In this case here, the Q will be 6,300. The change in temperature is going to be 95 to 11 which is going to be 84 degrees Celsius, right? So you press that in the calculator, 6300 divided by 84. You're supposed to get an answer of 75 joules per degree Celsius. Okay, then moving on to the final parts of this paper here. A solar panel receives sun at a rate of 5,000 watts. It's supposed to be 5,000 watts here. Thermal energy is transferred from the solar cell to a water with efficiency of 20%. So the solar cells can only absorb 20% of the power. Cold water of mass 15 kg enters the solar cell every hour. So it's basically 3,600 seconds, right? The specific capacity is this amount. Calculate the temperature increase in the water. Q is basically going to be MC theta. Theta will be equals to Q over MC. In this scenario here, it will be power times time. Power times time over MC. In this question here, the power will be 5,000, but it is only 20% efficient, so you're supposed to multiply by 0.2. Multiply by the time of 3,600, divide by the mass of 15 kg, multiply by the specific capacity of 4,200. Press all of this into the calculator. 5,000 times 0.2 times 3,600, divide by 15, divide by 4,200. You're supposed to get an increase of temperature by 57.1 degrees Celsius. 57.1 degrees Celsius here. Okay, and finally the last page here, last set. Yes, figure 5.1 shows a plastic cup. The cup contains sand, an electric heater and a thermometer. The power of the heater is 50 watts. The mass of the stand is 550, which is 0.55 kg here. The initial temperature is 20 degrees Celsius. The heater is heated up for 2 minutes, which is 120 seconds. The temperature is recorded until the temperature stops increasing. The highest temperature recorded is 33 degrees Celsius. So the change in temperature is going to be 13 degrees Celsius lah. Calculate the energy supplied to the heater. Yet again, Q is equals to... Oh, actually it's just power times time, right? Power is equals to energy over time. In this case here, energy is just power times time, which is going to be 50 multiplied by 120, which is going to be 6,000, right? 120 times 50. Yeah. It's going to be 6,000 joules, guys. Then, moving on, calculate a value for the specific heat capacity of the sand. Specific capacity Q is equals to MC theta. C will be equals to Q over M theta here, which is going to be 6,000 divided by 0.55 divided by the change in temperature, which was 13. So press that with the calculator. 6,000 divided by 0.55 divided by 13 here. You're supposed to get 839 joules per kg degree Celsius. 839 joules per kg degree Celsius. And finally, explain why the specific capacity of the sand may be different from the value calculated in A. Yet again, whenever we're dealing all the heat questions, all these formulas here are assuming perfect world scenario. The energy will always be less because the energy is lost to the surrounding. So you're going to say something like the heat energy provided by the heater is lost to the surrounding and conducted away. Okay, and this is how you're supposed to answer these questions here.